Where is the class rep? Not here. Please remind me at the end of the class to take attendance. I don't know now. I usually forget to take the attendance. 10:30. Okay. So we are going to continue from where we stopped in our previous class. I think we explained this, the Darcy's experiment, where he realized that the volumetric flow rate Q varies with the difference in head and inversely proportional to the distance traveled by the fluid and directly proportional to the area. At the end, we have this as the Darcy's law. I think I explained this in my last class. I went further probably and I started explaining about the hydraulic gradient, isn't it? And how the hydraulic gradient, or the relationship between gradient and hydraulic gradient. Although this I will change it because this is the gradient, not the hydraulic gradient. Okay, or it should be negative. Okay, it should be negative. So, what is the relationship between gradient and hydraulic gradient? What's the relationship between gradient and hydraulic gradient? As per our last lecture, I think I deliberated on that. And you were here, right? Oh, good. So, what is the relationship? Pardon?
Directions.
So, how are they related? Mathematically, how are they related? Mathematically. How are they related mathematically? Maybe the class rep will have to answer that question, given that he came late. He's the last to come. So your welcome question is, how is gradient and hydraulic gradient related mathematically? What do you mean by negative? Just saying negative, there is nothing mathematical about it. I need an equation.
It's the direction of greatest increase of...
Not definition, you are defining. Okay, let's hear the class rep. What is the mathematical relationship between gradient and hydraulic gradient? Which is what we discussed in a previous class, and you were here. So, what's the mathematical relationship between gradient and hydraulic gradient? J equals? No, I'm not asking you. Let him answer. J equals? Equals minus?
H dot.
The class did not review what we did in our previous class. He didn't review that. Yes. Over to you. I'm sure you must have gone over it and have reviewed it either now or before now.
But sir, the problem is that we are not having the same group.
Yeah, but you are supposed to be taking down notes. Even if you have it, my slides is usually just some bullet points. Do you get my point? You may not get, all the explanation in the slide. So, part of learning, you should learn to take notes. You should be coming with your pen and paper and be jotting down. Be taking notes. Because my slides, I just have some few points which will guide me towards what I want to elaborate on. Okay, so saying you don't have the presentation slides, that is not an excuse.
hydraulic gradient is equal to minus gradient times H.
Minus del H.
Yeah, minus the H, of course.
Okay. You see, I always go back. Probably I try to ask some few questions based on what we discussed in the previous class to see how serious you are. Because if, all these are very simple stuff, but if you don't follow it very well, really, you will get nowhere. Okay? This we discussed, we deliberated in our previous class at length, where we discussed the relationship between gradient and hydraulic gradient. And we mentioned that if we are to use J to designate the hydraulic gradient is equal to minus del H. All these are vectors, right? Which is equal to the negative gradient. Okay? And I think that was where we stopped, isn't it? In our previous class. From the terms in Darcy's law, I only explained the gradient, isn't it? And then show how it is related to the hydraulic gradient, which we mentioned they are all vectors, isn't it? Because you must have done vector calculus, although in our review, we reviewed only the vector algebra, but you did math 342 for those that graduated from here, where you did vector calculus. And the vector calculus you must have done the gradient as well. You must have done divergence of a vector, which is the dot between gradient, dot product. This is divergence. And you must have done call of a vector, the cross product. This is called call. All this you did in Math 342. And they constitute the vector calculus. Okay? So at one point in time or the other, we will find ourselves using some of this. Okay? We have started with the gradient. Later we'll go to the divergence, and probably later we may take the call. Okay? So all this you did in mathematics, but here you will find the real application. So that is that about the gradient. Now let's discuss about the area. The area here, in relation to the area, you were asking some questions about why is the flow rate not a vector, isn't it?
Yes.
You said it is supposed to be a vector. Okay, so let's start with that. Why is the flow rate not a vector quantity? Yes? Why must it be a vector quantity? Because you want it to be a vector quantity, isn't it?
Quantity and has direction, because the direction of the flow rate is within the pore space of the soil. It has direction, and vector
Flow rate has direction?
Yes, because it's following the
Are you
direction
sure?
of pore space.
Are you sure flow rate okay, let's start with the definition. What is flow rate?
Distance all over time.
Is the velocity over the area.
What?
The movement of the fluid by the area of that particular horizon.
The movement. If you don't, please don't demoralize me again. Don't tell me you cannot define discharge or flow rate correctly, please. At this level, no, it will be unacceptable for you not to be able to tell me exactly what flow rate is. It will be unacceptable. So, tell me what is flow rate?
Volume per time. The amount of water, the quantity of the water per time.
Yes.
The same definition, volume of water or fluid per time.
Volume per time. What is your definition? Discharge is the volume?
No, volume per time, yes.
Discharge is the volume? No, wait, let's get this. Is discharge the volume?
No.
Okay.
Speed by area. Speed by area.
What?
Speed. Velocity per unit area.
Velocity per unit area. It's called what? Discharge?
No.
Or flow rate?
Except velocity times unit
What
area.
what's the relationship between flow rate and discharge? You.
Relationship between
Flow rate and discharge. You see, every class I ask you these silly questions. No matter how silly they appear, they are fundamental questions that we cannot just overlook. No matter how simple, how elementary they appear, we cannot just assume that all is well. So what is the relationship between flow rate and discharge? This is hydraulics class, right? Okay, so I hope I'm in the right class. Hmm? No, now I'm asking something specific. The relationship between flow rate and discharge. Can you tell me?
discharge is equals to flow rate time.
What's the relation? What? Discharge is equal to?
Discharge equals flow rate over time.
Discharge equals flow rate over time. Any addition, subtraction, do you accept his definition? What? Oh, wait, what? No, relationship between discharge and flow rate.
It's the same thing.
The same thing.
Flow rate is the same thing as discharge.
It's the same thing as discharge? Are you sure?
Very, very sure.
Very, very sure. 100%. Flow rate is the ratio of discharge to cross-sectional area of flow. What's the relationship between volumetric flow rate and discharge? Volumetric flow rate and discharge. What? Volumetric flow rate?
It's still the same thing.
Is still the same thing?
Yes.
So why are other people getting confused? You are not supposed to be found wanting in something as elementary as this, really. Discharge equals flow rate. Simple, straightforward, direct. But for you to be telling me discharge equals flow rate over time, equals flow rate over area, equals this over that, no. They are just synonyms that can be used interchangeably. You can call it, that's why I even confuse you the more by adding volumetric flow rate to see if someone will now say, okay, now the volumetric flow rate probably is equal to discharge over volume or something like that. Different literature use different term to describe discharge, to describe flow rate. Sometimes they call it volumetric flow rate. Okay? Now, okay, so it all started when I asked you to tell me what is flow rate. So why do you think it will have direction? Someone defined flow rate or discharge as volume. Volume of what?
The volume of fluid that flows.
That flows or collected per unit time. Because how do you measure discharge? Probably when you open a tap, you have a container. You have, let's say, 20 liter bucket. You use your stopwatch, bam, and then start it. It will be flowing over time. It fills the container. Then you stop and see the time it takes to fill that container. Let's say it took 5 minutes. You have 20 liter. Okay, so the flow rate is the volume collected, volume of fluid collected over the time it took to flow, isn't it? So that is the discharge. So why do you think it will have direction? Thank God we have dealt with vectors extensively and scalars. So why do you think it will have direction?
This guy do not have direction. Because it only follow the direction of the container. I didn't think it has direction.
Okay.
And also,
Now that, yes, what do you want to say?
it's also the ratio of two
we will have another one, not called flow rate, but called flux. Now, we'll discuss about, okay, discharge or flow rate. Discharge. Or let me use flow rate. Or volumetric flow rate, to be specific. Volumetric flow rate. And then we'll talk about flux. Volumetric flux. We'll talk about mass flux. And then you also have energy flux. Let's briefly talk about these terms and then things will become clearer. You want to attach direction to the discharge, isn't it? But you are using the wrong term, which is the volumetric flow rate, okay, which is a scalar quantity. Okay, Q, discharge, okay? It's a scalar quantity and has unit or dimension L cube over T. And this we already explained, okay? Then you have what is called flux. Let me just define flux in general. What is flux? Flux. Want to tell me? Volume of fluid per unit area. Any other definition of flux? Flux is volume or the amount of a particular quantity or of a particular substance per unit area per unit time. Let me use phi to designate the amount, because I'm coming back to this. Amount of a substance flowing per unit area per unit time. This is, I called it amount, right? That is the general definition of flux. Flux. The amount of substance flowing per unit area per unit time. This area is the cross-sectional area and is perpendicular to the direction of flow. So flux is a vector quantity because it is specific. It goes in the direction of flow, in the direction of the flow velocity. So that is why I was saying, when you were hammering on why is the Q not a vector quantity, I said, okay, we will explain later. Because Q is not telling us anything about direction. It's just the amount at a particular point in time that we can measure that this is the volume per second. Simple. Or the amount we can collect per second. Has no bearing with direction at all. But flux has. Flux does have a bearing on direction because it's the amount of substance flowing per unit area, per unit time. And the area has to be the cross-sectional area perpendicular to the flow path. So that tells us something about direction. Hence, flux is a vector quantity. Are you following? But then this amount, this numerator that I called amount, could have many units depending on what you are dealing with. More often than not, when we are dealing with water, this amount, we call it volumetric flux because we are interested in the volume of water that is passing through a particular cross-section. So it becomes volumetric flux. Volumetric flux. And instead of amount, just vague amount, we will now have volume. Okay? It will now become volume over area passing per unit time. Are you following? Now, if you look at this as the volumetric flux, it will have unit. What will be the unit? LT, isn't it? The dimension of the volumetric flux will be LT, isn't it? And that same dimension is that of a velocity, isn't it? That same dimension is that of velocity. And this expression called the volumetric flux is what we also, because when you take these together, what do you have? What do you have? Discharge. You have the volumetric flow rate, isn't it? So the volumetric flux is basically discharge over the area, isn't it? Is that discharge over the area? That is the volumetric flux. And discharge over the area, we can give it many names. The first one, velocity. Any other name? Look at it very well. No, he mentioned velocity. Can you recall any other thing related to what we are discussing? No, just look at the formula. No. No. What we call the Darcy's velocity. This is the specific discharge.
Unit discharge.
Specific discharge. Are you following? This is what we call the specific discharge. It's essentially volumetric flux. And that is why, if you remember, I think I told you that we don't, we call it Darcy velocity, we call it specific discharge, and we also call it volumetric flux. And if you remember, this is what? A vector quantity, isn't it? It is what? A vector quantity. Okay? This is the volumetric flux. But then the unit is still LT. So that's why we call it Darcy velocity. It will be, that will depend on the area now. The area, the cross-sectional area of flow. If you have a pipe flow, in which the total cross-section is available for water to flow, then in that case, yes, the amount flowing through this cross-section, the discharge of that area will give you the velocity, isn't it? Because the total area is available for flow. Because even when you use the continuity equation here, you arrive at the same thing. Am I right? So in this case, or in this situation, this Q, which we call the volumetric flux, is now equal to the velocity of flow. Are you following? But then, when we now come down to porous media, where the area, the cross-sectional area, not all the cross-sectional area is available for flow. In that case, this expression, this volumetric flux, will not be equal to the velocity of flow. I'm connecting two things here. I'm connecting the discharge with the area correction, which is the next point. All that we are trying to do is explaining. Oh, did you bring my new black pen? Because this one is giving me, it's not very clear. What? Okay, you have another one? We are all trying to explain this expression. Yeah, that is E here, isn't it? Am I right? This is the Darcy's law, right? We have explained the hydraulic gradient. We are now connecting this with this and explaining them together. Are you following? So, for porous media, not all the area of flow, not all the cross-sectional area is available for flow. Hence, the volumetric flux is not equal to the flow velocity. Are you following? Although it has the same unit as velocity, but it's not equal to the seepage velocity, or what is called interstitial velocity. So in this case, it depends on the situation, isn't it? For open channel flow, for pipe flow, yes, the volumetric flux equals the flow velocity. For flow in porous media, no. But then what do we do? What adjustment can we do here? Let's go back to definition of what porosity is. What is porosity, by the way? Yes? What's porosity? Number? You have to be specific at this level. You have to be specific at this level. Because we defined it many times without number. What is porosity? Number of voids. Can you count the number? Okay, number of voids. Okay, go ahead. It's just the number of voids in a medium, right? Yes. Can you tell me what is porosity? He defined porosity as number of voids in a medium. So do you accept his definition? Volume of voids all over? Total? Volume of the area. You are still...
Volume, he's trying to say volume of total volume.
At this level, you shouldn't be found wanting. Even if you forgot about what porosity is, we have deliberated on that, isn't it? Yes. The slide is with you. So you cannot tell me that in this case I did not upload the slides, isn't it? I have already uploaded them. And for that matter, this is something that should be at your fingertips. All right. So porosity, volume of voids over the total volume, right? What is volume? It's usually the cross-sectional area times length, isn't it? And for the same cross-sectional area, we have, this is for voids, and this is the total area, but the length is the same, right? So we can also define as the area, cross-sectional area of the voids, or the total cross-sectional area, right? From here, the area of voids will now be equal to NA, isn't it? The area of voids will now be equal to NA. Now, let's go back to this. Let's go back to this. I don't want to clean this because I will come back to each of these ones. So far now, I'm only discussing, okay, we discussed about this. We are on this now, right? Okay. So, coming down to the Darcy's law and applying it for porous media, the area of flow here, if we want to relate it to velocity, if we want to have it in velocity form, by relating it with continuity equation, by relating this with continuity equation, This is the area of flow, isn't it? And the velocity, right? But the area of flow will now be given by NA, isn't it?
Yes, sir.
Are you following? So here, if you want to express the velocity using the Darcy's law and using the equivalence, then it's going to be K minus K over N minus K over N and then DH DL. Okay? DH DL. And in this case, Q, we define Q as Q over A, right? Isn't it? As Q over A. So Q in terms of this is going to be minus K DH DL. Isn't it? So basically when we slot it here, it is now going to be Q over N, isn't it? V equals Q over N. Okay? So, the seepage velocity is related to the Darcy velocity or the flux. That is why those that are very careful with terms don't refer this as velocity. They just call it specific discharge. And here, this morning, we call it volumetric flux. But this is the actual seepage velocity or the interstitial velocity for porous media. But we say this holds when you have open channel flow, when you have pipe flow. But it doesn't hold. You cannot call this velocity in porous media because of the area correction. But in this case, the area has been corrected using the effective porosity. And here N is not just the total porosity, it's the effective porosity which we described before as the interconnected interstices through which flow takes place, or you have continuous flow. Okay? So we already mentioned that this is a vector, isn't it? Our volumetric flux. Because it's taking care of the direction of flow. That is the one that is taking care of the direction of flow. It has the same direction as the velocity of flow, isn't it? This we explained before. So discharge alone or flow rate alone as volume collected or passing a particular section per unit time, it doesn't say anything about the direction. And that's why it is a scalar quantity. But the one which is a vector quantity, which is telling us something about the direction, is the flux, which is the discharge per unit area, per unit time. Or discharge per unit area, because discharge is volume over time. So discharge per unit area is now the volumetric flux, because that area is a specific one, perpendicular to the flow path. And the flux is in the direction of the flow velocity. And that is a vector quantity. Whereas the discharge or flow rate alone as it is not a vector quantity, but a scalar quantity. Are you following? Now, let's move on to another flux. This is the volumetric flux. When dealing with contaminants, yeah.
That relationship, what do you call it?
What?
V is equal to K over N. You call it a name. You can't get a name.
Seepage velocity, or interstitial velocity, or average flow velocity, or average linear velocity. Different texts use different terms, but these are all the names. But it's the actual velocity of fluid flowing through a porous media, not Q. That's why Q is just, called Darcy's velocity or specific discharge, and now we call it flux. Are you following? Now, when dealing with contaminants, we are not so much interested about volume, because as we are going to learn, probably if time permits us, when we will start to discuss about solid transport, we will realize that our interest when it comes to contaminants is mass, not volume. The mass dissolved, because concentration is what? Mass dissolved in a particular volume of water. That determines the concentration, which we call, in another term for fluid, mass density. Mass over volume, isn't it? So for contaminants, we are so much interested about the mass dissolved in a particular volume, which is the concentration. So in that case, instead of using the volume density, volume flux, for water, we're interested about the volume flowing. And that's why we use the volumetric flux, or Q, or specific discharge. But when dealing with contaminants, we are so much interested about the mass, not the volume. Because the volume could be misleading in terms of contaminant. And that's why even it is expressed in terms of like density, mass per unit volume, because that determines the concentration of the contaminant. So in that case, we will be using the mass flux. And in this case, don't forget our general formula for flux, amount of substance, isn't it? Over unit area over unit time. For volumetric flux, the amount is what? Volume. When dealing with contaminants, the amount will be mass. Mass probably in gram, kilogram, and what have you. Usually in kilogram. So you will have it as the mass flux, which probably will be kilogram per meter square per second. This is the mass flux. Okay? And the mass flux usually is represented using J. What do we use J for? Hydraulic gradient, isn't it? And I told you in some texts I is used, isn't it? But here we are avoiding I, because I, we just finished Cartesian unit vectors. And I is the Cartesian unit vector along the x direction. Okay, so we dropped I and used J. But unfortunately, once we will start to discuss about solid transport, the same J we are using here as hydraulic gradient, we will use the same J as the mass flux. Or we will just call it flux. Okay? Because already this one we call it here specific discharge or what, but in the real sense, it is called volumetric flux. But we will refer to J as just simply flux. But in essence, it is the mass flux. Because it's kilogram or mass. Mass is M. L minus 2T minus 1. This is the dimension. Okay? And as we are going to define it, you will see that, and it's also a vector quantity. All the fluxes, all these fluxes are what? Vector quantities. Because they are specific with respect to the direction of flow of the quantity. Okay? All the fluxes are vector quantity. So this is also a vector quantity which could be given mathematically in terms of contaminants. We are going to see, we will use it as CQ. We are going to see whether Q is the Darcy velocity or the interstitial velocity when we reach that point. Okay, but it's mathematically given as C is the concentration of the contaminant. Or sometimes it's given as the density, because whether density, whether C, they all have the same unit. But don't look at density as if it were the density of water. Okay, so when looking at for contaminants, we use C. But the unit, they are essentially the same. Concentration is mass per unit volume, isn't it? Density is mass per unit volume. Okay? We use density basically for water, and we use C for contaminants. Are you following? Now, that is the mass flux, which we will just simply call flux. Okay? And then you have energy flux, although it's out of our scope, the energy flow per unit area, per unit time. So instead of mass here or volume, you have energy, probably kilojoule or whatever. Okay. Yeah, C is the concentration of contaminants. Okay? So now we have related A and Q, isn't it? And we have seen that we need some modification, isn't it? We need some modification for the area, because the total area is not actually the total area available for flow. So we have to substitute this with something like this, isn't it? Okay? So now, let's move on. I hope now you understand why discharge or flow rate is not a vector quantity, but flux is. Okay? Flux is. Yes?
I have a question with regard to this flow rate, not a vector quantity.
What?
I have a question.
Okay.
The example is that it is a drop of water per time.
Yes.
But since we are now dealing with the groundwater,
Yes.
assuming the same water
Yes.
volume,
Yes.
B,
Yes.
within a time T,
Yes.
at an inclined angle,
Yes.
does that not depend on the vector quantity?
No. For water flowing through, let's say, an aquifer, you have a section, let's say this point, 1. You want to determine what is the amount of water flowing per unit time, and that's it. It doesn't tell you anything about the direction, whether it's flowing this way or that way. You just want to know what is the quantity, the volume in meter cubed or whatever per unit time. Simple. Has nothing to do with direction. Even in groundwater. But then direction comes in when you're talking about flux. When you're talking about the mass flowing per cross-sectional area, per unit cross-sectional area, per unit time. So that is now a vector quantity, because the cross-sectional area has to be perpendicular to the flow path, and the flux has to be in the same direction as the velocity of flow. And that now takes us to Q, which is a vector quantity, which is the volume flowing per, or the discharge per unit cross-sectional area. So this is a vector quantity, which if this is the flow velocity, the flux has to be in the same direction as the flow velocity. So this is a vector quantity. While just discharge is just at a particular point, you just want to know the volume that is passing by, whichever way, whether this way or that way. Just the volume at that particular point in time, at that particular point in space. Simple. Yes?
What if we are considering it in the context of pipe fluid, and this has a specific direction, now the discharge? So do we categorize it as a vector quantity?
It's the same, because this can be an aquifer, it can be a pipe.
But in this case,
Yeah.
in pipe you have a specific direction it's moving.
Yeah, in that, but we just want to know the amount passing. It can be this direction, it can be that direction. We don't know. And we're not interested. We only want to know the volume. Simple. But for the flux, the volume passing a particular area, and that area is specific, perpendicular to the flow path. All this, when we come to some derivations, they will play some important roles. Okay? Now, going back to our Darcy's law. Now we explained the hydraulic gradient. We explained the relationship between the volumetric flux and the seepage velocity. At the same time, we explained the relationship between gradient and hydraulic gradient. Now we'll move to the hydraulic conductivity. Hydraulic conductivity. if you look at the way it was written here, the flux is giving us this dot del H, right? You can see some, underline here. Did I mention about, did I say anything about the hydraulic conductivity?
No.
In my last class?
Just define it.
Okay, yes.
You define it.
Hmm?
You only give us the definition.
I only defined it as what?
The ease through which water passes.
The ease with which water passes through the void spaces, isn't it? As hydraulic conductivity. Okay? And it has unit LT, right? Same unit as velocity. Yes.
The energy flux. I don't get the explanation of the energy flux.
Yeah, energy flowing per unit cross-sectional area per unit time. Amount of energy, which is in joules, kilojoules, and what have you. Okay? That you may do it when you are considering certain thermodynamic properties of fluid and what have you, which is beyond the scope of our class here. Yeah. But just explaining generally what flux is. Okay? Flux is generally amount of substance. The amount. That amount could be volume when we have volumetric flow rates. It could be mass when we have mass flux. It could be energy when we have energy flux. Is that clear? Now, for hydraulic conductivity, we define the hydraulic conductivity. And did we define isotropy and homogeneity? Yes, we did. Oh, okay. Then we are just good to go. We define isotropy as what? What did we define isotropy? Can you refresh our memory?
When Kx
equal to Ky equal what?
K.
Equal to K. That is when the hydraulic conductivity is a single scalar value in space, isn't it? It's not dependent on any direction. Then we say that it is isotropic. And this is also true for other aquifer properties like porosity. Because porosity can also be used to describe or to explain isotropy or anisotropy. Okay? But here, because we are talking about hydraulic conductivity and porosity largely remains virtually the same. The variation in the components are not significant. So, more often than not, we don't use n to be a function of x, y, z. We just use a single average deterministic value for porosity. But for hydraulic conductivity, the resultant horizontal hydraulic conductivity is somehow different from the vertical one. And for that reason, we don't usually ignore that difference in the components of the hydraulic conductivity. And that is why for anisotropic aquifer, we have to have 3 values at every point in space for the hydraulic conductivity. It will have 3 values. 3 values, or it will have values dependent on the x, y, z axis. Because I will have to correct myself by saying 3 values, not just 3 values. But this underline that we have here, this double underline, is because it is a tensor. Tensor. Second rank tensor. Second rank tensor. We have 0 rank tensor, first rank tensor, and second rank tensor. We even have third and fourth rank tensors. But hydraulic conductivity is a second rank tensor. For 0 rank tensor, they are scalars, scalar quantities. When it is isotropic, Kx equals Ky equals Kz equals K. A single value in space, isn't it? So that is being treated as a scalar, just single point, single value, which is zero rank tensor. When we have a vector, this is a vector, right? Which has three values. This is a vector. It has three components in space, qx, qy, qz, isn't it? This is a first rank tensor, which has three values. First rank tensor has three values. And vectors belong to first rank tensors. And vectors, as we know, because more often than not here, we use only one coordinate system, the Cartesian coordinate system, but you can have other coordinate systems, the rectangular, the polar coordinate, the Euclidean, and what have you. But vectors are not affected, irrespective of the number of coordinates or the type of coordinate you use. It will have three values, except that the values could change from one to the other. And then you have the second rank tensor, where the hydraulic conductivity belongs to, and it has 9 values. 9 values. The second rank tensor, which, how do we differentiate in writing? In writing, usually now, scalars, you know, they are unbolded first characters, okay? But vectors, they are usually, they are written in small caps, small letters, and bold, and italicized. But tensors are bold, in capital, not italicized. Okay? So, second rank tensor has 9 values. 9 values. 9 values. Kx, z, kyx, kyy, kyz. Nine values in space. This is second rank tensor. Third rank tensor will be 3 to the power of n. 3 to the power of 3. How many values? Fourth rank tensor will be 3 to the power of 4. How many values? 81. And you have other quantities that belong to the third rank tensor and fourth rank tensors. Okay, but here we are talking about hydraulic conductivity, which is a second rank tensor. And this is synonymous with the stress tensor that you did in mechanics of materials, even 3 or 5, isn't it? These are cross terms, right? These are cross terms. Let me depict these 9 values on a cube of fluid. This is a cube of fluid. If I am using the right hand rule as my coordinate directions, this is y, x, z. So here, oh no. Then here is going to be yy. These are the 9 components of the hydraulic conductivity depicted on a cube of fluid element. But as you can see, here there is something very important that I will need to explain. First of all, these are called the cross terms. You can see them. These are called the cross terms, while these are called the principal terms or the principal directions. The cross terms for second rank tensor, it is isometric. Sorry, it is symmetric. And by symmetric, it means kxy equals kyx. Okay? So in that case, instead of 9 independent values, you will be left with 6 independent values, because this will be equal to that, this will be equal to this, isn't it? And this will be equal to that as well. Okay? So I'll be left with 6 independent values. This is in 3D. For 2D, you will have it to be kxx, kxy, kyx, kyy. Right? In 2D. But then, this is the Cartesian coordinate system. When the principal axis, these are the principal axis, isn't it? When they are aligned with the Cartesian coordinate system, the cross terms will cancel out, isn't it? Because this is orthogonal. I mean, this, and this, they are all orthogonal. It's 90 degrees that is between them. So when it is aligned to this, when it's aligned to the Cartesian coordinate system, the cross terms will cancel out, meaning they will become 0. Okay? Meaning for aligned isotropy, because this is anisotropy, isn't it? This holds true only when you have an anisotropic medium. If it is isotropic, you have just one k value, isn't it? Simple. But if it is anisotropic, you will have to have this. And then, if the anisotropy is aligned, the meaning is that this is aligned to the Cartesian coordinate system, so you only have the principal directions are aligned with the coordinate, the Cartesian coordinate system, so we will only have the diagonal values. The cross terms will become 0. Okay? And then you will be left with something like this. You will just have kxx, kyy, and kzz, and any other term, here, they will all become 0, isn't it? And then your matrix is somehow simplified in that way, because probably you may need to perform some operations, this with a vector, isn't it? Because Q equal K dot del H, isn't it? Am I right? And don't forget, this is another vector, right? Which will have 3 values. So when performing the vector operations, when you have just diagonal matrix, so it makes the computation easier. Are you following? Okay. Any question before we move on? No question. Now we'll take some few minutes break, and when we come back, we'll continue with our presentation. All right. So I think now this is the flux vector, written in terms of the tensor, hydraulic conductivity, and the gradient del H. Oh, I think I need to push it back. Okay. Yeah. So this is the slope, H1, H2. Now, okay. This is the volumetric flux, just as I finished explaining. And then this is the average linear velocity, isn't it? Which is obtained by correcting the area, isn't it? By correcting the area, and instead of using just n, just a, we multiply the area with n, because that will give us the area of the voids, isn't it? And this we call the average velocity, used for calculating average velocity of contaminant transport, and called average linear velocity. And the assumptions inherent in this formulation is that the flow is laminar and the aquifer is saturated. Okay? And the aquifer is saturated. Should anything change from these assumptions, then a lot will change in the formulation as well. As simple as the saturation. Okay? Fortunately, probably time will not allow us to really look at the unsaturated area or unsaturated zone. We can still express our Darcy's velocity, but then we'll have to modify some things when we are applying the Darcy's law to the unsaturated area. Okay, so this expression is valid when the flow is laminar and the zone is the saturated zone. That is very important. Now, hydrogeology is three-dimensional because you have your aquifer, you have, flows in almost all the directions. Okay? When we look at this cube and try to represent the velocity, we have Vz, that's the vertical flow, and we have Vx and Vy. If you remember our vectors for the horizontal plane, we can find a resultant horizontal velocity, isn't it? Which here we call Vh, which will be equal to what? Vh will be equal to what?
Vh.
Yes.
Vy plus Vx.
Will be equal to Vy plus
Square root of Vy square plus Vx square.
square root of Vy square plus Vx square.
Vh square will be equal to Vy square plus Vx square minus Vy Vx cos.
What? Can you go over it again?
I'm going to use the resultants of the two.
Okay, I just want to know the expression for Vh. I just want to know, how do I find Vh? One said Vx plus Vy, the other said Vx and Vy should be in square root and all squared. And what say you? Okay, I don't know what that means, but just tell me what is Vh. Simple. Given your knowledge of vectors.
I said Vh squared is equal to Vy squared plus Vx squared minus Vy Vx cos angle of Vh.
Have you taken? Do you all take? Did you take the review of vectors with me, all of you? And did you go over the lecture notes and everything, the examples? Although I didn't give you any reference book, probably. I only gave you my slides, but now probably I will post a book that you can expand your knowledge, or you can have some more examples and even exercises on what we reviewed as per the vector algebra. The book is a statics book, which like I told you, is just a topic in statics in the CVN 201 that you take. But the way our CVN 201 is structured, it goes straight, to the analysis, the reaction supports, analysis of structures, the truss analysis, the beam analysis, and what have you. Okay. So I will post a reference. I will post the e-copy of the book. Okay. It's just a chapter. It's in chapter 2, which reviews the vector algebra. So probably for those that are serious or that would like to lay hands on more examples and understand the concept better, and if possible even solve some exercises, Because it's only through solving exercises that you will be more confident. I mean, you will be, rest assured, you will have confidence about the extent to which you have learned or grasped a particular concept. Okay, so I will do that hopefully today. But I wasn't, when I asked this question, sincerely speaking, I wasn't expecting anyone to tell me anything different from the correct answer. It is just, my teaching method that it has to be interactive, and for that, I can ask you the simplest of questions so that at least instead of you just listening to me, you will also talk, isn't it? So I never expected anything different from the correct answer. I just asked, for asking sake. But unfortunately, to my greatest surprise, I am having different answers. And it's only one that should be correct, isn't it? I know if I will ask each one of you, I will even have more options. That I know. That I know. We took our time to review the vector algebra. All these are vectors, isn't it, in 3D. So for the horizontal plane, there is even a particular one similar to this, which we solved when deriving, the sum of the components and what have you. When you have a vector in 3D, you have the horizontal plane, you find the resultant of the horizontal plane, and now use that, very simple, straightforward, and direct. All these are vectors. I say when you have vectors, the resultant is simply the sum of those vectors. If there are 2, if there are 3, irrespective of the number, the resultant is just simply the sum of those vectors. Here we have the horizontal plane, which has 2 vectors, Vx and Vy, and they are all vectors. And we have the resultant, Vh. So Vh will simply be the summation of its component along x and y, isn't it? Which is Vx plus Vy. But some have they misunderstood Vx and Vy to be scalars, to be the scalar components of Vh. And for that reason, they thought it would be the magnitude, this and that. They are all vectors. So it's simply the addition of the components of Vh. Simple, straightforward, and direct, isn't it? So now, vertical flow. Apart from Vh, we have Vz, okay? So, and now V is the overall resultant. And V will be given by what? What? V, this V will be given by what?
Which one?
This, yes. V plus Vz, isn't it? Simple. You see, we are just applying the parallelogram law here. That's why we constructed this cube around all the sides. This is the vector that we have, but these are the components along x, y, z. The horizontal plane has a resultant, okay, which we use with this one to get this one. So V is simply Vz plus Vh. Simple, isn't it? And I hope you did not forget how to formulate the Cartesian vector forms of the vectors, the different methods that we did. Don't worry, I'm not going to ask you for any, because I may rest assured that I'll be in for great surprises. Okay, but it is good if you practice it and understand it. Okay, because we will be using these terms, or sometimes we'll be using the principles. Okay, in our formulations. So vertical flow is important in field of investigation. This is the velocity. Okay. More often than not, you don't usually have flow vertically, but sometimes you do. But it's so small compared to the horizontal flow. Do you understand? So, but the vertical flow is important in field investigations when we are considering vertical flow of contaminants. Contaminant flow usually vertically, depending on the source of contamination, isn't it? Sometimes undergraduate storage tanks, sometimes leachate from landfills, sometimes due to anthropogenic activities, industrial activities, and what have you. It infiltrates from the unsaturated zone. That is the first port of call, isn't it? And then it goes to the saturated zone, isn't it? And then depending on whether it is L Naples or D Naples. Have I mentioned anything L Naples or D Naples before? At the beginning of the class. So I hope you can recall what I said about them. Okay? So depending on whether it's an L Naples or D Naples, then it floats on the water or it goes down to the aquifer bottom or to the bottom of the aquifer. Okay? So all these are vertical flows. Okay? Although vertical flows are so small, I mean the magnitude is way smaller than the horizontal flow, but they are also important that in some instances we cannot ignore them. What am I saying? So in some instances we can just ignore the vertical flow and consider it to be horizontal, okay? But there are instances in which we have to consider all the components of the velocity, okay? And then in delineation of recharge and discharge, all these happen vertically, and groundwater and surface water interactions, all these happen due to vertical flows and interaction between adjacent aquifers. Okay, all these also happen due to the vertical component of the flow velocity. Oh, we are still with our vectors, right? So vectors and vector components. The vector velocity. This is a vector velocity which has three components: Vx, Vy. In matrix form, it is represented this way. In coordinate form, it's represented this way. In vector form, it's represented. Did I write it here? Okay. How do I write it? How do I write this in vector form? The components. In vector form. Yes?
V is equals to Vx plus Vy plus Vz.
V, the vector is equal to Vx plus Vy plus Vz. Right? Is he right? Correct.
Yes, with the arrow.
Okay, with arrow. Oh, you are busting my bubbles. Why do you always have to bust my bubbles? When I am confident that you are going to tell me the right answer, you all gave me the wrong one.
I refuse to put the unit vector.
I said, this is a vector, right?
Yes.
Expressed here using the coordinate, here expressed using matrix. So I want it expressed using the vector form. And you are all telling me it's just summation of the components, the scalar components.
VZK.
But that is why it's not in vector form.
No, he said with the arrow.
That is meaning vector form. If you are
I said he should give me in vector form. They are saying is the sum of the components. This is half arrow already. So what are you telling me?
Him is trying to say putting arrow on each of the coordinates.
But these are scalar components.
You have to put your IG.
The vector will be Vx in I direction over the modulus plus.
How determining this thing?
Oh.
VXI plus VY VZK.
Haven't you seen something like this before, please?
Yes.
Is this not what we call the vector representation? So why are you eliminating the IJK and just telling me it's Vx plus Vy plus Vz? What? But this Vx and Vy and Vz, they are not in vector form. They are the scalar components, isn't it? So I'm just asking you to give me the vector representation using the scalar components as it is. This is using the coordinates. This is using the matrix form. In vector form, the same components, you will just add IJK and then sum them up, isn't it? Is that clear? You see, I'm still going over what I took my time to go over, but it is obvious that you didn't really digest that material. You didn't digest it well, isn't it? All right. You better go and do it because it is still not yet over. It is still not yet over. We will still be going back to those materials. Okay? So it's better you go back and study it. Like I said, I will post the book. It's an e-book which you will just download it free of charge. Okay? And then if you can go over it and study it. Okay? In addition to the slides that you have. So Oh. Okay. The same thing for the vector. You see here, this is the horizontal component, and this is the vertical component, Vz. Okay? And this is the overall resultant velocity, which is made up of two components, Vh and Vz. And we call it average linear groundwater flow velocity, which we said is very small, isn't it? What is usually the representative value of the groundwater velocity? Any range you can think of the groundwater velocity?
0.2 meters per second.
2 meters per second. Wow. Wow, wow. Please convert 0.2 meters per second to meters per day. Do that. Tell me. 0.2 meters per second to meters per day. I want it in meters per day. Converted. Anybody? Is anybody done? What? 720 meters per day. That is 0.7 kilometers per day. Isn't it? 0.7 kilometers per day. Wow. So our groundwater.
17,280.
What?
It's 17,280
meters per day.
But that is 17 kilometers per day.
Yes.
17 kilometers. From here to Zaria City, I think the downtown will be about 17 kilometers. Yeah. From here, I mean from this point I'm standing to Zaria City downtown, it will be about 17 kilometers. So it means groundwater flows on the average from here to there per day.
I'm not sure.
It is about your unit. I told you we don't forgive when you use the wrong unit, isn't it? It is about the unit that you use. The numeric value, you are right, but the unit is wrong. It's not meter per second, it's meter per day. We usually express the groundwater flow velocity in meter per day because it's so small that in one day, it moves so slowly. About 0.2 to about 0.4. So you can imagine. Okay, by the way, can you show me what a meter is? Is it like this, like this? Or from here to there? Or
No, this is just 100 centimeters. 1 meter.
where? Okay. So this time around, my bubbles, you didn't burst my bubbles. Okay? No, it's really important because sometimes you ask students, okay, what is 1 kilometer? He will tell you probably from the north gate to Kwangila is 1 kilometer. It means he has no idea what a kilometer is. Or if you ask 1 kilometer, sometimes they will say, okay, from the bottom, from the floor to the ceiling is 1 kilometer. So we must be able to relate all this. And that's why I was converting the meter per second to meter per day. Sorry, to meter per day. So that you can imagine the speed with which the groundwater is moving with. Okay? So it's very slow. Okay? It moves slowly. I ask this because sometimes, you must have link between theory and practice. You are taking groundwater flow velocity. Probably some of you probably may have their thesis in that area. And when presenting, somebody, on the flow, he will not be interested in all the results you are displaying, all the mathematics you did and everything. He will just ask you, what is the average groundwater flow velocity? And then you will be shocked. you will just be grumbling and don't know exactly what to say. And this means that, there is huge gap between practice and the theory. Because what you did was to go to the field, maybe measure this, measure that, but you failed to relate it to what actually happens in practice. So at all times, you must relate these two. You can go to the field, you can do all the calculations that, you can have, but then you must have the practical significance, the practical meanings of everything you do, most especially as it relates to your thesis. Okay? Now, the volumetric flux, and thank God, you see here I represent it as volumetric flux, isn't it? And with my earlier explanation of what flux is, now, it will become clear to you, isn't it? And that's why you see I'm not even referring to it as Darcy velocity, because it is in essence a volumetric flux, which is also a vector quantity. So what are we doing here? We are just representing the components of the vectors, the volumetric flux and the velocity, isn't it? And then the same thing like we did, that is the velocity vector scaled by porosity, which is a scalar. Okay? So the same thing here, it will have the horizontal resultant and then the vertical one, or the overall resultant, okay? Which we call specific discharge or Darcy flux or Darcy's velocity. Now, hydraulic gradient. I explained what a hydraulic gradient is, isn't it? Although here I'm going, this is the gradient, right? This is the gradient, the hydraulic gradient is the negative, isn't it? So this we are talking about the gradient, and it's a vector, isn't it? The direction is upward. Why is it pointing towards the opposite direction of the velocity? This is the velocity, right?
Because it's negative and because it's a greatest decrease rate.
Greatest
Decrease rate.
decrease rate. The gradient.
This is hydraulic gradient.
No. Which one is the hydraulic gradient?
The one pointing upward.
Is the hydraulic gradient?
No, this is the gradient. This is the gradient.
Pointing towards the direction of what?
Greatest
Greatest increase, isn't it? Which is upward, isn't it?
Yes.
Downward is greatest decrease. Am I right?
Yes.
Okay. So the same thing, because it's a vector, so it will have the components and then the vertical component as well, isn't it? Which is del H by del X. The hydraulic gradient will be the negative of this, isn't it? So that's why simply we just refer to it as, but I will just edit and put the negative, or to call it gradient vector. Then you have the horizontal component and you have the gradient, okay? Now, let me still ask you something. What will be the direction of the hydraulic gradient? Yes. The hydraulic gradient. Yes. Opposite, isn't it? Good. Because J is minus del H, right?
Yes, sir.
So, if this goes this way, del H, then J will go the other way, isn't it? Simple. And this is all from the definition of vectors, isn't it? So you can see why it is important to go and review vectors. We couldn't have really got these concepts clear without reviewing the vector algebra. Although, like I said, we are still reviewing. We are still reviewing, and we are adding the vector calculus gradually. So it means that the hydraulic gradient. Okay, let me ask another question. Sorry, I asked too many questions in a class, isn't it? But like I said, if I don't ask questions, probably I will just turn around and find more than half of you just sleeping. But when you talk, then, you will have to open your eyes and make sure you understand what I'm doing, because, you can be the next person to answer the next question. Yes, my friend over there, the last person. Awal, right? What will now be the relation? How will you describe the relationship in terms of the direction of the hydraulic gradient and the velocity? Yes, and velocity. How are they related? Using in terms of direction, hydraulic gradient and velocity.
They are in the same direction.
In the same direction.
Yes.
Do you agree? Okay. You got it right. They are in the same direction because we have already shown before, isn't it? This is the direction of the velocity, isn't it? And this is the same direction of the hydraulic gradient, which is pointing towards the direction of the greatest decrease in head. Okay? All these, little questions, they are very important when it comes to even, let's say, solving problems, numerical, and for those that may be working in the field or having anything to do with groundwater. They are very important in understanding the basics. Okay? My time is up. And we have come here where we are going to learn how to evaluate the hydraulic gradient. We have understood what the hydraulic gradient is in theory. Okay? Now we will learn how do we evaluate that. Probably in the field and using some numerical values. Okay? So tomorrow we'll continue from here. Okay? So any question before we call it a day? No question? And just like I have started discussing with the HOD yesterday, we may try to round up before the end of this month.